everyone, my name is April and this is Bash Course Quarantine Statistics. Today we're going to talk about probability. Personally, and I think a lot of you would agree, this is one of the most confusing topics in stats. Hopefully this video will help you review the basics and figure out how to attack problems. The basic idea of probabilities is figuring out how likely an event is to occur. Here's a list of vocab and ideas to keep track of throughout the video. The fundamental idea in probability is the law of large numbers. In the short run, you can't always guess what an outcome is going to be, even if you know its probability. But in the long run, that is, after infinite tries, proportions of outcomes are going to become closer and closer to the proportions given by the probability. Let's first look at the basic probability rules you probably learned in previous math classes. The first one is on the AP formula sheet. The probability of one event happening or another event happening is the probability of those events added. We subtract the probability of both happening so we don't double count them. It makes more sense if you look at a Venn diagram. When I'm adding P of A plus P of B, I'm adding the center part twice, so we just need to subtract one of those out. The probability of one event happening and another happening, an intersection, is the probability of the two events multiplied. But there's an important caveat. It only applies if these two events are independent. When two events are independent, the outcome of one does not affect the outcome of the other. For example, it makes sense that the probability of being in the heavier half of the population is not independent of the probability of being in the taller half of the population. But it's not always so easy to tell. This often means you should not be using the simple multiplication equation in an AP problem unless it tells you that the events are independent. I'm going to discuss other problem-solving strategies to consider before going to that rule. There is actually a way to determine whether two events are independent, if the probability of A given B is equal to the probability of A is independent. A way to know that two events are not independent is if they are mutually exclusive or disjoint. Disjoint events can never happen together, so naturally if one occurs, it will affect the occurrence of the other. Dependent events open up a whole section of probability called conditional probability. One of its most basic ideas is on the probability of A given B. Given is written by a straight line. Its equation is actually on the formula sheet. The probability of A given B is equal to the probability of A and B divided by the probability of B. Often we look at A and B and automatically go, oh, that's just A times B. Don't do that unless you know they're independent, right? Another equation can be found by going back to that AND equation. We're going to kind of derive it. Remember that if two events are independent, the probability of B given A is the same as the probability of B. So if you know they're independent, you could substitute P of B with P of B given A in the AND equation. What you've done now is create an equation that could work even if the events aren't independent, because it asks for B given A. Often if you're going to be using that, you're given a two-way table. It's pretty easy to use by making fractions out of the table. Seriously, don't trip yourself up by overthinking. That's a common mistake. However, many problems don't give you one, but you should still try to represent the sentences they give you visually, especially when you're not even sure how to start a problem. Likewise, formulas probably shouldn't be the first thing you do. So you can use a Venn diagram like I showed before, maybe a two-way table, or a tree diagram, which is really common. You should also be looking for signs that the problem is about a binomial or geometric distribution, which I'm going to discuss later. So, tree diagrams are used when you're given some conditional probabilities. Here's an example. This data is not real, like always. A research lab claims they have developed a quick, cheap, new COVID-19 test. They decide to test it in a large area where they know that 9% of all people have COVID. Preliminary findings show that the test gives a false positive 2% of the time and correctly diagnoses COVID in 97% of the people who have it. What's the probability of getting a negative test result if you don't have COVID? How many people in a group of 1,000 from this area would you predict to get a positive test result? What's the probability of having COVID given that you tested positive? I'll be drawing a tree diagram because I know the result of the test is conditional on the presence of COVID in a person. So if I were to pick a person in this area at random, this dot, we have two options. They have COVID or they don't, 9% and 91%. Now each person gets a test. What does a false positive mean? It means that the person does not have COVID, but the test says that they do. So that branches off of no COVID. What does a correct diagnosis mean? A positive result for a person who does have COVID. So 0.97 and 0.03 branch there, making sure that you're labeling to keep it clear. Great, we've made a tree diagram. Now comes the interpreting part. Before we go to what the problem is asking, let's check we understand the diagram. What does 0.03 mean using our vocab? That's the probability of getting a negative test result given the presence of COVID. So we can do that for our other numbers just to have it in our brain. If we were to multiply 0.91 and 0.98 together, what does my result mean? That's the probability of not having COVID and getting a negative test result. We'll do that for all the branches. It's a good thing to do. So the problem asks the probability of getting a negative test result if you don't have COVID. So that's the probability of negative and no COVID, which we already calculated to be 89.18%. Then, how many people in a group of 1,000 from this area could you predict to get a positive test? Getting a positive could mean positive with COVID or positive without. So we'll add the 8.7% and the 1.8% to get 10.5%, which is 105 out of 1,000 people. We're all done. For the last part, we're going to apply our given equation and the result of the previous problem to get 83%. There are a lot of different things you could be asked about from a simple setup like this one though, so keep those different options in mind. Now we're going to talk about binomial and geometric probabilities. In addition to what I mentioned, you may also be asked about describing a binomial or geometric probability distribution, transforming variables, or combining variables or statistics. So adding, subtracting, multiplying, means and standard deviations, and then think about SOCs for describing, skewed, outliers. It's some of that information is on your equation sheet. Both of these categories of probability include a binary sample space for one trial, either success or failure. An event occurred, success, or it didn't, failure. This success must have a set probability that doesn't change trial to trial, and the outcomes of each trial must be independent of each other. The difference is that in binomial situations, you're given a set number of trials. Geometric situations involve doing or observing trials until and including the first success. We remember these characteristics using acronyms, BINS for binomial and BITS for geometric. Binomial settings also have a specific equation which you can find on your formula sheet. The geometric equation is more intuitive. So let's look at an example. At a certain large grocery store, the probability of a customer wearing a face mask on a given day is 0.68. When you go to the store, you pass within 6 feet of 11 other customers. What's the probability that all 11 were wearing a mask? How likely is it that 8 or more of those people were wearing one? And what's the probability that you come close to your first person with a mask after coming close to 5 people without one? First, identify the variables. P equals 0.68 and equals 11. For the first two questions, we know it's binomial because each of those encounters is considered a trial. And there are exactly 11 of them. It just tells us. For A, x equals 11. We can just input that into the equation as such, or into the calculator with binom PDF, making sure you show your work, not just binom PDF and labeling your numbers. We get just 1.4%. Then it asks about 8 or more. One way you could do this is repeat what you just did, replacing 11 for 8, 9, 10, and 11, and add those probabilities together, the probability of 8, 9, 10, or 11 with masks. But that takes too long. So we just use binom CDF, where the C is for continuous. When you put X into Binomial CDF, it'll tell you the probability of getting X or fewer. When you put X into Binomial CDF, it'll tell you the probability of getting X or fewer. So to find the probability of X or more, do 1 minus that probability of 7 or fewer. Let's read the next question. What's the probability that you come close to your first person with a mask after coming close to 5 people without one? The first thing to notice is that this is geometric. Why? This time I didn't tell you there were a certain number of trials that occurred. We stopped counting the trials only when a success occurred. So what's the success here? It's seeing someone who doesn't have a mask. So its probability is 1 minus 0.68, 0.32. We want to know the probability of getting 1 and 2 and 3 and 4 and 5 people without a mask. That's 0.32 to the 5th power. You also have one person with a mask. So you also have one person with a mask. That's 0.32 to the 5th times 0.68 to the 1. So you've created that equation intuitively without having it on the formula sheet. Luckily, we can do this on our calculator with Geom PDF. Probably going to want to do that. P is 0.68, the probability of someone wearing a mask. And X is 6, because we want the probability that the 6th person you see is the first one to have a mask. We got 0.0023 both times. Okay, that's it for now. Let me know in the comments if this was helpful and what you would like to see in the future. Keep practicing and good luck on the AP. Till next time.